Okay, so you have seen some rather simple examples where we have a polar equation turn out to be a very, very simple rectangular equation, such as polar equation turning out to be a linear function or a circle function. So here, this is probably a more complex, a more time-consuming example, where we have a simple polar equation, and we're going to find that the rectangular equation we get from it isn't as clean, if you want to use that word. So we have r equals 3 sine theta tangent theta. Remember, we have a couple of our conversion equations. We have x squared plus y squared equals r squared. We have y over x equals tangent of theta. And we have x equals r cosine theta and y equals r sine theta. So keep these in mind as we're looking at converting. So looking at this, the goal here is to substitute in x and y. So I'm thinking that r would be really nice to have an r squared. So I can replace that with x squared and y squared. If I multiply by r, so I don't want to square both sides, because having sine squared, tangent squared, looking at my options really doesn't get me anything. So rather than squaring both sides, I'm just going to multiply both sides by r, because then I'm going to have an r sine theta, which will work out. Let's see what we get. So we multiply this side by r, we multiply this side by r, we get r squared. Now be cautious on this side. You might be thinking distributive property, distributing the r to the sine and the r to the tangent. But I want to tell you that we would only need to think distributive property if there was addition or subtraction between these two terms. This is actually one whole term. For example, thinking of this as x times y instead of x plus y. Okay? How that makes a big difference is when I multiply by r, it's just 3r and then sine theta tangent theta. Okay, that r is only there once still. Okay, so now let's work with some things. R squared we can substitute for x squared and y squared. All right, I see here an r sine theta, which we can replace with a y. Tangent theta, oh, well, tangent of theta, we can replace with a y and an x, y over x. Okay, let's simplify a little bit. 3y squared over x, okay. Now, we're trying to get y equals, we have a y on both sides, so let's first get our y terms on one side. So we're going to subtract y to the right side. So that would give us x squared equals 3y squared over x minus y squared. Okay. So I'm not going to square root right now because that would give me x equals, which is not what we want. So do you recognize what we could do with the right side? If there's anything that we can do with the right side? You might notice that there's a y squared term in both. So we can factor that out. So we have x squared equals y squared multiplied by 3 over x. And since I factored out a y squared, we would have a, not 0, we would have a minus 1. Minus 1 because of the minus up above. Okay, so now probably things are a little bit clearer of what to do from here. So we're going to divide both sides by this. So we get y squared equals x squared divided by 3 over x minus 1. All right. Now there's a couple things that we can do because we're not quite done yet. We don't like the idea of having a fraction within a fraction. So you could get a common denominator and then multiply by the reciprocal. You can do that. That will work. But if you've been following along in these lessons, you know, I believe we learned this in the trig identity unit. You know that if I want to remove a fraction, that I have to multiply the top and the bottom, the numerator and the denominator, by the denominator I'm trying to cancel. So I'm trying to remove this over x. So if I multiply both numerator and denominator by x, what we get from that y squared equals, okay, we would get x cubed. All right, now if I multiply the denominator by x, we would have 3x over x, which would just simplify to 3. And then we would have to distribute, so this x would go to the first and the second piece. So we would have minus x. Much nicer, isn't it? Isn't this much nicer than this piece here? And then lastly, to get our full rectangular equation, positive negative square root of x cubed over 3 minus x. So because we had the square root, you should be screaming, this is not a function. And you were to be right, this is not a function. I believe it's not only is it not a function, but there's actually a point here where this would be discontinuous, where we would have an asymptote. So thinking of that. And also this would be a point where you have a restricted domain, because we can't have a negative within the square root. So if you want to just graph this, you can, just to see what it looks like. This is a perfect example of how, in some cases, polar equations look much cleaner than their rectangular counterpart. But sometimes it's the exact opposite. Rectangular looks cleaner. So this is just an extension off of what you already had watched with the basic converting equations. Hope this helps with just extending your understanding, and I'll see you in the next lesson.